Okay. Got a red light showing this time, which means that after only 6 or 7 weeks, it might actually be recording this one on video. We'll find out. So today we're looking a bit at service-oriented architectures and a bit about on the web services stack, which is one of the ways of implementing those. And then, depending on what happens at the end, we might drift into next week's, the beginning of next week's one, or we'll see where we get up to in time. I was originally hoping to squish a bit of next week's ones into this one, but this one's pretty full, but we'll see how we go. Right, SOA, web services. Let's see where we start from. That's a good point to start with. Now, I'll probably say several times, the word service, the word services are grossly overloaded terms. What happens in this industry is something becomes popular and all the marketing people say, if we had that feature, we'd be able to compete. Therefore, take out the rubber stamp, we've got that feature. So, in doing so, the meaning of the word morphs. See, well, I suppose if you squinted hard and you could say that was service-oriented. Great, well, thank you, we're service-oriented. So, the meaning of some of these words is very hard to pin down just because the marketing people have been at it. And so what started off being a very clear idea in someone's mind has been sort of mulled and is now a bit more general. So, the word services means lots of things. Here we're talking about a particular meaning of it, of services and of service-oriented architecture. The IaaSes, the IaaS, JSS, etc., they're all cloud computing terms, and the S in all those acronyms all means service. But we're not talking about that. That's coming up in about 2 lectures' time. We'll start talking about infrastructure as a service, platform as a service, function as a service, etc. Of course, they're all cloud topics. If you have this lovely stack of this is what our system looks like, all the way up, then we're talking about that top layer just there. The idea of having applications that you've written and exposing them to the outside world as a service. That's the meaning of service we're talking about. Yeah. So it's just that top layer today. And next 2 weeks' time, we'll do the various AASs. And yeah, marketing. Word du jour, the word of the day, was services for a while. Right. What's a service mean in this context? We'll go through a few definitions. Let's try that particular Wikipedia one down the bottom. And I'll come give much more definite definitions in a minute. But the idea is it's a lump of functionality, a self-contained, discrete lump. The top part says a logical representation, in other words, a computer implementation of a business activity. It does something meaningful. It says repeatable, meaning if you call it multiple times, it does the same thing every time. That's good. And examples in it: check customer credit, get a weather forecast, consolidate account details. They're large lumps of business logic which have been packaged up into a chunk. Self-contained. Internally, they might be made by composed of other services. We take a bunch of services, put some glue stuff around them, and expose that set of services as a service. That doesn't matter. To the consumers of the service, it's a black box. It's something with a defined way of talking to it, and it does certain things. So some type of contract there. The Wikipedia, undoubtedly, that's changed 15 times as Wikipedia. Some other people decided they could explain it better. But here we've got the same idea. Loosely coupled, so they're just lumps that are not, don't have strong dependencies in each other. Functionality, self-contained. Each service implements at least one action, does something, such as, and some examples. So we have a self-contained lump of something or other that exposes services to the outside world and it performs actions for you. So the common features of a lot of these definitions are coarse-grained chunks of meaningful business functionality. Coarse-grained, and I'll mention later, coarse-grained because this is going to be distributed computing, and what kills you in distributed computing is the performance hit you get by having chatty protocols. Lots of messages going backwards and forwards. You want nice, chunky, meaningful bits of functionality. The service provides some abstract implementation interface, and you don't know or care how it works internally. You don't know what it's written in, you don't know how it works. You just know that it does this for you. And then you build up your larger scale applications by integrating sets of services together. So you compose services from services. And it really is just the distributed computing we've been talking about over the last few weeks, but what you needed to do to make that work on an internet scale. The plumbing will be based on standards for interoperability, and we'll talk about one set of those standards today, perhaps two, and the whole architecture of the system has to reflect the reality that we saw, the problems you get with large-scale distributed computing that we've talked about. You're going to get unreliable components. You're going to have network failures. So when you're doing this composition, you need to reflect that reality. Particularly, you need to worry about trust boundaries and security. Trust boundaries we've talked about. There are protocols and things you could do if you trusted your partner. If you don't trust them as much, there are things you shouldn't do because that's opening you up to attacks. And in practice, what we're going to want to do is take bits of existing code and turn them into services. We'll put a service layer, a service wrapper around them. And now that functionality, which was encapsulated in a piece of legacy code, is now being turned into a service that other applications can integrate into their functionality. So lots of wrappers, lots of adapters, possibly brokers. Some of the stuff I talked about last time about composing business services and workflows fits in here as well. The bits we're calling, those components, could be services, and we then can build workflows around that, and you don't really care where those services are located. One of the guys originally pushing this is a entertaining bloke, if you ever get to see him present. Don't know if he does that much anymore. A guy called Don Box. Do some searches, web searches on Don Box, and there's a presentation where there's the SOAP song, which is quite nice. And the SOAP is a protocol we'll be talking about, and he's one of the writers of the SOAP protocol. So there's one of the presentations where he does a song about soap, and apparently I haven't found it, but there's a presentation he gave in a bathtub. So he likes having skin in the game for his presentations. It makes them quite amusing. So here's one of the guys behind this definition of services and the protocols back 15 years ago, and this is from one of his pieces of text, which I used to have a URL to it here, but it was from MSDN, Microsoft Developers Magazine, and they archived all their articles prior to 2009, I think. And now you can get them, but you've got to download them as compiled help files, so it's a bit harder to get at. But you can find those articles if you look around. So service orientation says, well, we've built a lot of distributed object type of computing, distributed component computing models, and he did work on Microsoft's com and decom. He wrote a couple of well-used books on that, and so he knows what he's talking about in that area. So take the lessons they learned from implementing components and distributed computing based on components and do it again. Except this time, having learnt all the lessons, there's a comment in one of his things saying, yes, well, if we're doing it again, we wouldn't do that. You learn these things the hard way after you spent 5 years developing something. No, we made those decisions wrong. So here they're trying to do distributed computing with internet-based protocols again. So we want to service-oriented development, focus on systems that are built from a set of autonomous services. Each one of those services is a program that interacts using message exchanges. We talked about messages last week. And the individual services are built to last, so we're going to have defined contracts for those services, which you're not going to be changing rapidly. So you have to worry about evolution of services, and then, worth trying to find the original of that. And that link that I did leave there is a discussion back there, because of some of the stuff I'll talk about later. I'll talk about when I talk about the politics of some of this. And this is a guy, it's worth reading, Schneider, talking about some of the politics and why some of these ideas are sound ones, and people who think that they're not sound ideas probably don't understand what the ideas were about. So, but in all these technological developments which are done out in the open, there will always be discussion. And there will be different points of view, and it's worth understanding that. So, service-oriented architectures. That's an architecture based on services. That's straightforward. It's the architecture that you're going to use for a services-based world. And in this world, we have applications that are providing services, applications that are consuming services. The applications share standards. They're built using common standards. The networking messaging protocols are common. They share contracts saying, I will do this functionality. Here's how you ask me to do this. When you ask me to do this, I will do this in response. So the contracts, the interfaces we've talked about before, and the schemas, which are, if I'm sending messages around the place or complex data objects, this is what they look like, the schemas. And they share nothing else. Not implementation technologies. It doesn't matter whether you're doing this Java or .NET or .NET Core or Rust or whatever you're doing. It doesn't matter. It's all defined by the standards, the contracts, and the schemas. And that comment is there. This probably comes from Don Box, those words. Because previous attempts were things like, well, Don Box talks about when he was working for Microsoft early on, they had this idea of taking their binary protocol, the one that COM is based on, OLA32, and implementing that everywhere. So he was responsible for working with a team to port OLA32 everywhere. And they eventually decided that was a really horrible idea. And then Java came along. And Java says, we've got great portability, you just need to adopt a common language and a common runtime, and everything's portable. So in that case, you're sharing implementation details, you're sharing jar files, you're sharing lots of implementation. And this services world says you don't share any of that. It's all black box, you don't look inside it. So some of that discussion for Schneider is referring to these 4 tenets, four rules that Don Box wrote down and publicised, that with services, the boundaries of a service are explicit. This is the service, it's this. It's rectangular, that's the service. Hit microphones. It has explicit boundaries, going into a service means crossing one of those boundaries, and that has a cost. A networking cost, a security validation cost. There are, in crossing boundaries, crossing borders, costs. So you have to be aware of that. So those borders of things like security costs, trust, and performance that comes from those. Services are autonomous. You don't necessarily control them. If you're calling on an Amazon service, Amazon has defined their services, they've defined the schemas and contracts for their services, but you don't control it. You can call on it, you can ask it to do things for you, but you have no control over it. Amazon could say, well, we're moving from version 3 to version 4 tomorrow. Be ready. So they can do that because they're autonomous. All that you share with a service is the schema and contract. The contract owners define the contracts and the schemas, and that's all you know about. Other than that, it's a black box. And the last one's a bit puzzling. This is a nice to have, and it's reflected in the standards we'll be talking about, that policy-based attributes are really good. So wherever possible, you want to move stuff out of code. Code is a bad place to put things. You want to put business logic in code, not lots of other stuff. So related to this cryptic comment is when you look at the Java or the .NET, C#, etc. world, there are a lot of things that are done by attributes. Now there's sort of the square bracket something or other. So I'm not writing any code, but I'm specifying the behaviour, the context in which this will be done by giving hints to the language and to the runtime. So I'm moving things out of code and pushing them somewhere else. And in that world, I can also take things out of the code and push them into a config file. So then I can change the behaviour of a piece of code just by going and editing a config file, and boom, next time it starts up, it behaves differently. This is related. So if I want to do security, I want to do authentication, then I shouldn't be writing code which takes care of the authentication. I should be somehow in my contracts, in my service definition, saying, and this service can accept the following 3 methods of authentication. You must use one of these. And then that's a policy that's attached to the service definition. I require my service callers to be authenticated, and these are the methods I will accept. And then the code inside the service doesn't have to write the code that handles the authentication, because the environment the server is living in knows what you will accept and will do the handshaking for you and take care of all the security interfaces and just pass you a validated authentication token. So your code can be very much simpler, and the whole problem of negotiating mutually acceptable security protocols is not your concern. So we've moved it from your code into a policy and a matter of policy negotiation. And we'll see some examples of that. I'm just going to have an aside. I always meant to do these things at the beginning and then get started. So the assignment 1 is up, been up for a couple of days, due end of next week. So I was trying to work out what the dates were, because last year had Easter and things, and the dates were all sort of mucked around because of Easter. So due at the end of next week. I'm working on the group assignment. I had some what I call technical difficulties. The bits of code won't compile for me. So I'm expecting to have that finished probably by the end of the week, but Monday at the latest. So expect it to be up on Monday morning. And when I put that up, I'll have Alan also put up whatever you need to be able to sign up into the groups for it, groups of 3. And it's just another implementation thing, except this time you've got a bit more work to do in the implementation and a whole lot of architectural justification about why you're doing what you're doing. Okay, now I've remembered to say that rather than at the end thinking, oh, and the other thing, speaking about bureaucratic stuff, E1 is on an emergency family trip back home, wherever home is. So we'll try to get, those of you who are in E1's shoot group can move to one of the others until he's back. So he could have sent me an email on Sunday night saying, I've got to leave the country tomorrow morning. So if you're in E1's group, he's not here today. He will let me know whether he's back next week or not. Good. Now we'll return to our scheduled broadcast. So, principles of SOA. You're building large-scale integrated applications from services. You want your services to be coarse-grained and rich. Chunky. That's the word. I like using that word. Not chatty, but chunky. So, make a booking. Don't search the Amazon catalogue and return things that like this. You don't do something like get a result set from Amazon and then go back and pick up read an item at a time from it in a nice chatty protocol. You go and ask it to do something and it gives you a meaningful size result back because you're trying to minimise network round trips because they're expensive. And each of those services should be big enough, all the architectural things. It should be not too big and not too small. It should be just right. So specialised enough to have a clear focus. What's this do? It's not the Amazon shopping experience service. You look at the Amazon stuff, which we'll touch on later, then you'll see there's about 40 or 50 services they're providing because that covers all the functionality they want, and each one of them is big enough to be able to do a meaningful chunk of work in a single call, but not so big that it's too broad and it doesn't make sense. It's nicely clumped to be a meaningful chunk. So, clear focus. Think about reliability and robustness. Reduce dependencies because it's just a chunk. You probably don't want to rewrite legacy code that works, so that's where a lot of wrappers will come in. You might write a piece of C# or Java code that takes care of the service interface and then drops a request onto a message bus to an older application that does the job and then sends a response back. You don't know or care from the outside world that it's just a wrapper onto a piece of code that's been around for 20 years because it does the job. And general advice, keep everything as simple as possible, including, of course, all the technologies you're using. And at the end of this lecture, you might wonder whether we've managed to achieve that. So there's an example that might be in Ian's book. I must dig up that chapter and have a look at what I wrote there. But there's a distributed application that we've seen before, and we've got lots of bits and pieces. Everything's connected together in some horrible graph, and the red lines here are things that we probably want to do using some type of web services protocol. So how they work outside doesn't matter, but these are independent services provided by independent organisations, and we just need to talk to each other, and why wouldn't we use some type of standard there? You could build that whole system using Java messaging, but then the credit card processor and the bank and the suppliers have all got to use the same Java messaging provider. Or you could use MQ or MSMQ, but then the same problem exists. You want a single common protocol that's going to be supported by all the platforms that you want to be able to use. So that's an application just glued together, locally written, third-party, external applications, using all types of platforms and technologies, bits of it running everywhere, and using a standard services protocol. Cool. Okay. now we're going to get stuck into the, if your eyes glaze over with the technicalness of this, it's okay. What we're not going to be doing is saying exactly what does that thing in the angle brackets mean here. The purpose of this stuff is to get the gist of what it is, not to worry about the technicalities, because no one ever sees most of this stuff. The only time you'd ever see any of this stuff if you were doing some debug traces and wanted to look what was flowing on a wire, because it's all hidden by the people who've gone and written the frameworks. So, web services protocols. Most of this lecture, probably all of it, apart from where I touch on other things, we'll be talking about what's sometimes called the WS star service protocol set. WS Web Services stack. And it's all XML based. The messages we pass around are all XML based. The services are all defined in XML documents. If we're passing messages and documents around, they're XML, and it builds on other XML standards as well. So wherever possible, they're using existing XML standards. And as people say, they're all human readable, if you're a particularly strange type of human. In other words, they're all just text format. And they're all possibly carried over HTTP, the web protocol, but that's not part of the standard. There are other bindings. You could pass these protocols across other communications protocols if you wanted to. And the standards are managed through W3C, but of course W3C is interested in standardising what goes on the wire, what's passed between the participants over the network. And they're not interested in programming models or APIs or anything like that. They're just interested in what's going on the wire. So part of the controversy here has been these things are called web services standards, and there is nothing there. Well, the things there which are vaguely webby are the use of XML, but XML has nothing to do with the web particularly. HTTP is a web transport protocol that the web is built on, so there's a bit of webbiness there, but that was done originally for ease of going through firewalls. And the World Wide Web Consortium with a standardisation body, so a bit of web stamp of approval there. So that has caused some controversy over time, that here is a thing which calls itself web services and it's not very webby, and we'll come back to that. The history of this protocol stack, it started off as a simple XML-based remote procedure call protocol. That was the initial implementation and had a name. So it was just, we can build an RPC protocol and we can do it entirely in XML and we can pass it over HTTP. Can we do that? And Don Box was one of the guys who did that design. He said it took them 3 days. At the end of the 3 days, they were finished it. So that was version 1. And then that was seen to be successful, and then people said, let's build on this and build yet another complete distributed computing platform. This would be number 382, I suppose. So there's IOIP coming out of Corba, there's several from Microsoft, probably IBM have probably got their fingers in some of them, there's DCE, there's been any number of complete distributed computing stacks. This is yet another one. So we take that very simple XML-based RPC protocol and you start adding capabilities like the ones we saw in lectures 2 and 3. So you're going to add capabilities that real applications need. So security, reliability, robustness, routing capability, addressing transactions, etc. And when you do all that, they also move away from RPC models to messaging models, because messaging models are more effective in many ways, more flexible. And that gives us a standards called WS star. That whole standards development standardization process was driven by Microsoft, IBM, and a few others. There's a group called Oasis involved in standardization as well. And I expect that's what made these standards different to every other set that had gone before it. Because this time, all the major players were working together instead of competing. And before it was like local federal politics. If you have a good idea, we're opposed to it because it's your idea. That's the way the world was. Here, all the major players realised that they weren't going to be able to win. They needed to. Interoperating was more important than trying to be the sole provider. So, great cooperation, particularly by Microsoft and IBM. And Sun tried sabotaging it for a while and eventually came on board as well, which is good. Interop, widely available, supported, and at the time there was a lot of complaint from the web people who go and build web pages, who think that they know about the web, and they really got annoyed that the W in WS stands for web. They said, this is not all webby. And that's led to a different way of approaching these things called REST. And REST I'll touch a little bit further on today and next week as well. And the answer is they do different things, and you can use both. And in that spaghetti diagram we had before, some of those are probably going to be WS star and some will probably be REST, and that's okay. They can both coexist because they really do quite different things. And when I talk about that next week, there's a really nice little chart from Microsoft, because obviously Microsoft support all of these things, and they say here's when you want to use these, here's when you want to use these. And these things in the middle you can do either way, and that's fine. A bit of terminology, because I know what these words mean and I might just use them. So we have messages, requests go from a sender to a receiver. On the path, they can pass through intermediaries, which are other nodes in the system, applications, probably, that receive a message and then pass it on. So they're intermediaries. There can be any number of intermediaries between the sender and the ultimate receiver, which is where the message is finally going to end up. And the sender doesn't know about the intermediaries, it just knows an endpoint to send a message to, and it has no control over what the intermediaries might do. They can take the message, reformat it, add things to it, combine things, and that's all cool. So as part of your architecture, you can have senders, receivers, and intermediaries. I've got a really nice example of that. I just have to remember where it is. It involves the tax office and such. So, the WS standards. There's a wiki page there, which is only about that long, and lists all the W star standards and all the XML standards and all the web standards that are dragged on. And it just goes on and on and on. And you obviously don't need to dive into all of those, and your brain will melt if you try reading them anyway. If you've tried reading standards, you'll understand that. And a lot of them are there because if you want to implement this, then you use this standard. So, for example, with security, there might be WS security, but it uses authentication standard and da-da-da-da-da. So in order to write this standard, itself is made up of elements from other standards. So they're not all ones that you'll actually see. So, it allows intermediaries to talk to intermediaries. It allows extensions. So there are optional header elements, extendable header elements. The normal sort of webby model, if I don't understand something, I can choose to either ignore it or throw a tantrum. Everything is in XML. All those XMLs are defined with schemas, and we pass attributes in SOAP headers. Let's look at some more of that. But before we do, I've been saying we're going to do a full distributed computing stack. If we go back to lecture 1 or 2, we did introductory distributed computing, and all the distributed computing is about is really 3 things. I want to be able to find something. In the Corba world, I might be finding an object. I might, J2E and decom world, I might be finding components. In this world, I might want to find a service. So I want to find the entity which is providing the service. I want to find out its interfaces, its schemas, its contracts. So find out what information it needs to do its job, find out its address, things like that. I want to be able to ask it to do something for me, call a method, invoke a service, whatever, and then add a few really useful, what we were calling ilities. So we want to be able to probably provide transactional support of some form. There's a whole lot of security things we want to provide. We might want to provide reliability, robustness as well. And that applies to Corba, .NET, J2E, and to these web services standards. That's what I meant by a complete stack. We want to be able to find things, find out about the things that we've found, and ask them to do something for us with a few very useful, rich services attached to it. We'll come back to some of the others things in a few minutes, but we'll start off with calling things. In this world, we use a protocol called SOAP to call things. SOAP originally stood for Simple Object Access Protocol, but as of version 1.1 or 1.2, it officially doesn't stand for anything, it just stands for SOAP. So it's no longer an acronym, and you might say it never was particularly simple anyway, so that's good. So originally it was just a remote procedure call using XML, but there were mechanisms for passing messages as well as doing RPC calls, and they've now deprecated the RPC, and it's really just a message passing protocol. It consists of envelopes, headers, and bodies. That's what each request and reply looks like. It's an extensible protocol. You can add new header elements if you want to, and widely used, and is up to version 1.2, and it's been 1.2 for a decade, and I can't imagine it ever changing. So SOAP 1.2 is what there is. That's what a SOAP message looks like. Not an XML. We have a SOAP envelope. That just marks the beginning and end of a message, just wraps it. We've got a header, which is optional, and the elements in that header are also optional, but they might be mandatory because we've negotiated a particular thing using policies. When we've negotiated, they've now become mandatory because we said we are going to provide this authentication token on all our requests, in which case that's where those authentication tokens go. So, and then we have a body, which is the actual message document that we're passing along for the service request. So there's an example. So we're running this over HTTP. So we're using HTTP. We're doing a post command to a stock quote service running on stockquoteserver.com. It's in XML. I didn't bother counting how many characters it was, so that's just in an L. And then we're going to be calling a SOAP method called getLastTradePrice, and then we have the SOAP envelope, which contains nothing apart from the SOAP envelope and the terminating SOAP envelope, but it also contains the namespace for SOAP. Then there's the SOAP body. There's no header in this message, and we're going to be calling on getLastTradePrice. It wants a parameter called symbol, and symbol is DIS, and here's the response. Again, coming over HTTP, it's an XML, There's the envelope, SOAP namespace again. There's the body. There's the response message, which is a message called get last trader price response. And that particular namespace, and it's 34.5. That's it. That's a real SOAP message and response. It always seems like a lot of characters to pass DIS and 34.5 around, but that's life. There were two encoding styles. DocLit is the standard one that's used these days, and so we've got a document schema. The XML body is encoding of that document is in the SOAP body, and that's just what people use these days. The original RPC model is now deprecated. So there's a lot of characters there. You might think, oh, this is going to be painfully slow. And, well, processes are fast these days, and we have lots of them, so that's not necessarily too bad a problem. But there has always been objection here. This is a really verbose protocol because of all the use of XML. And the question is, well, is it really that slow in practical terms? Compared to, say, binary alternatives, is it really that slow? And it depends a lot on the number and size of the messages you're passing around, and your application protocol, and the amount of time taken by the transport protocols, and network delays and speed of light. As I said before, speed of light is really slow. It'd be nice if we could get version 2, but it's a bit hard. So these were, I'm very familiar with this work because I was one of the people who did this work, and these slides have been included in here, and I thought, oh, I take them out. Oh, no, it's cute enough. So we had a project called CENTI, Centre for something or other in Information Economy, and let's play some networking games and applications on the networks. And we were interested in SOAP and other protocols, and we had this question of, well, are they feasible or are they too verbose? So we thought, well, let's go and build some applications and test them. And so we did that, and we measured single thread call latency. So we do a service call, it goes off over the network to a service, and we get a response back. So we measured the call latency. And we had small, medium, and complex messages. That's cool. And we just ran it. The first set of numbers are all local, and we're just running on 100 meg LAN. That's fine. Intel servers, and we measure some of the factors in the performance. And that nice graph is what we got. Now let me explain a few things. We've got 3 commercial products, 3 commercially available, I should say, SOAP stacks. One of them was Tomcat Apache. One of them was, I think, Sun's implementation. I don't think it was IBM's. And the other one was Microsoft's. They're A, B, and C. And I don't know which one of the which is which because we had to mask them for publication. But I do know which one is which in terms of performance. And we compared that with .NET Remoting, which is a binary protocol which is the predecessor to WCF in the .NET world. It's a nice conventional binary protocol. And there's MSMQ, which we've talked about, message queuing. And you see that we've got, and the fact, well, there's two things here. You'll see in general, the RPC Inc. convention, which is the one that's now been deprecated, is slower than the DocLit one. There's just more overhead that has to go through in the stack to do that, which is one of the reasons why it probably got deprecated, because it was inherently insufficient. The other thing to note is that these three implementations are different. Some of them are much worse than others. That is not a problem because we're interested in what's the protocol capable of. So the best implementation is what the protocol is capable of. The other implementations are just capable of improvement. So if we look at these, and we'll do the simple one, we've got 1 millisecond, 2 milliseconds, 4 milliseconds, 4 milliseconds, and we don't have a docklet for B because they didn't support it. So we're going from 1 to 2 to 4 milliseconds. There's not much in it. If we go to the medium, we've got 10, 17, 7 and 10. So that particular SOAP implementation is the same performance as MSMQ and only slightly slower than the binary highly tuned .NET remoting. So that's okay, and then we go up to the larger messages where the XML overhead might be more significant. We go 20, 15, 29. So for the large messages, docklet for A is faster than MSMQ, which is a binary protocol, and only again a little bit slower than the binary protocol. So I'd say from that the protocol's fine. Now, there's a bit of overhead, but not worth worrying about. This is locally over a LAN. The only thing I do remember about which is which here is that the fastest one was the Microsoft stack. And I think the slowest was the Sun one. So, and Tomcat. Tomcat was pretty terrible. Tomcat and Apache was pretty terrible. But it just means that someone hadn't put the effort into tuning the code. It's undoubtedly a lot better. So on that you say, well, it looks clunky if you look at the protocols, but effectively they're just fine. Let's talk about that. What about WAN? So we had a network available. We had a fibre link to Canberra of our own. So lightly loaded gigabit network, no contention. So here we've got the Microsoft and Apache stacks and a very simple, basically the same application test. And this is just with the medium sized message. Now, what this is a histogram of response times. Okay, so we go and do the Tomcat Apache, crank up that particular client, and we do that calling it 1,000 times, and we measure all the response times and we just plot them. So this is a histogram. So the Tomcat Apache TA is giving me about 37 milliseconds round trip, and it's about 3 milliseconds or so speed of light time. So down here is what you can do in the fibre. Then, so that's the TA SOAP, it's the bad one up there. So that's been deprecated. The RPC is slower, and we go up here, and here we've got funny situation. We've got some MSMQ a little bit slower, and the other MSMQs are about 10 milliseconds, 11 milliseconds, along with the Microsoft SOAP, and over here is about 8 milliseconds are all the two binary protocols. So it's again about 30% slower, which is not bad for all that chatty XMLness. So that was just something we did, and says the performance is fine. In case you get people saying this stuff is too verbose, we don't want to do that. But everyone uses XML, everyone uses web protocols, so they're used to very verbose messages. Okay, going back to that distributed computing 101, we said the first thing I said was finding things. Well, you want to be able to find things. I want to call Amazon. How do I call Amazon? Where do I find what services Amazon has? And in that web services grand view, there was a protocol called UDDI, Universal Description, Discovery and Integration, which was again a web service in its own right. So it was a service that you could call into. You notice I'm using past tense. So, and it had things called white, yellow and green pages, and the vision was that there would be a single universal directory. I want to go and call a service for Blur, I want to find Amazon's services, or I want to find services for online shopping, whatever. I would go and find it. Or there might be trade associations. You know, the automobile manufacturing industry might decide that these are services, so we will host a set of service specifications, and we'll do that. So that's what UDDI was about, a single universal directory. It never took off. People tried various versions of it. Mostly people these days will either use local UDDI, so if you're getting a Microsoft Web Services stack, then there'll be UDDI there, so you can set up a local UDDI, but the global one's never taken off. People either use local repositories of their own, they will go and deal with, if you want to go to Amazon, you go to Amazon, and they'll tell you what services they have, and you can download a file. And then other functions of it are a bit supplemented by DNS as well. And how do you know where things are? Well, DNS will tell you how to get to a server. So it's a nice idea, it just never took off. And don't read this. I just put that there for completeness. I mentioned white, yellow and green pages. That was the grand model as well. That's just meant to be a sea of words that you're not supposed to read. There we go. But it does introduce another word. So that's that overall model that's involved with UDDI. The word it introduces is WSDL, which is the Web Services Description Language. So in this model, you'd go and call on the UDDI service registry and find out about services. This is you as the service requester. You go and ask the UDDI directory. It finds things and gives you service descriptions back that you can then go and call on a service provider to use. The service descriptions which are held in there and that you use and are provided by the service provider are written in WSDL. So that's the overall model. But that top part is really clunky, and that's the way it is. WSDL, second point of the Distributed Computing 101, finding out about things. Web Services Description Language, and of course, it's an XML description of a service. The interfaces, methods, parameters, etc., requests, responses, how to bind to the service, and is typically generated and consumed by tools. So in the Visual Studio IDE you're using, you can say, well, here's some stuff, go and generate my interfaces as WSDL. And it will go and take your interface definitions that you've written in C# and go and create a WSDL definition of those that you can then export to someone who wants a WSDL definition. Or you can consume it. You can say, I want a link to a service, here's its WSDL definition. It will take the WSDL and turn it into a C# definition of compatible service. So that's all good. And WSDL looks like it's got ports which describe the operations that can be performed and the messages are involved in those operations. And why it's called port, I don't really know. It's got messages. Messages are made up of parts. You've got type definitions if you want to do complex types, and bindings, which are message formats and protocols for each of the ports. So there's the same thing in XML. That's the overall structure of a WSDL definition. Some limitations of WSDL. WSDL is fine, if a bit unreadable for what it does. It's a single service definition. It's the simple request response definition only. It's an IDL just like all the other IDLs are, except in this case it's an IDL interface description language, IDL, for web services written in XML. But there are equivalent IDLs that Microsoft use for COM and DCOM. There are equivalent IDLs in the CORBA world. All of these distributed computing platforms have had an IDL because you need to be able to define abstractly what the interfaces are of the things that you're trying to call into. So, yeah.
So there's the port types defined in the WSDL structure.
Mm-hmm.
So I got confused by, so to call the SOAP, we get into a server through a port. After that, we carry a port type on the XML.
No,
what?
Okay, let's see if we can answer that question by looking at some of the examples. Okay. What WSDL doesn't do is specify application protocols. None of the things we've looked at so far specify application protocols. You know, what order you must call the services in order to achieve a complete. If you're shopping at Amazon, you must do this, this, and this, and then you can go and, once you've got a shopping cart established and you've got items in it, then you can go ahead to purchase them. But there's an order in which you must do things. If you're doing a general purchasing thing, you must go and get quotes, and after you've got a quote response, then you can send a purchase order, and once you get that, then you might get an invoice back again. There's an application protocol there of quotes and invoices and purchase orders and shipment orders, etc. None of that's in here, and none of that is in any of the standards really. There is a language called BPEL, which I mentioned a week or two ago, and theoretically one could do that, but I don't see much. The business orchestration people have been interested in trying to do this a bit, and some of the work that Alan and I were doing was working in this space, but it doesn't seem to be particularly interesting to the practitioners, and the academics aren't interested in it either. Some more bits of the standard. There's a standard called WS addressing, which is how you define the address of a service. And they're basically just URIs, Universal Resource Indicator. UI indicator? I think so. That's an odd word to use. They're basically just extended URIs, but you ship inside messages. You ship these around, so you need a standard for defining them. You say, well, why do we need this if we're just using HTTP? We've already got the web URIs, URLs. Well, the stuff is transport neutral. You may not be able to rely on that. So if you're using carrier pigeons, you need to define how to do WS addressing endpoints with carrier pigeons. That's okay. But you could do that. And there's no constraints on them. You can construct, partition services however you wish. So, WS address, an endpoint reference. So WS addressing endpoint references. So we've got some namespaces. The first and third are just boilerplatey ones. We need the addressing namespace because we're going to be doing addressing things. If we didn't have the first namespace there, we wouldn't be able to use the addressing tag there because we wouldn't know what it meant. And we're going to be doing policies later on, so we need the policy namespace. So we drag in all that part of that standard as well. And then we're doing weather forecasts, so we'll go and use our weather forecast namespace as well. And the actual address is an HTTP address, and it's at HTTP example org/weather/US. That's the address. And then reference properties which are attached to the address to know which actual endpoint we're getting to is we're going to go to the services weather wind info endpoint and combine all that. That's the actual address. And then we can attach policies. We'll talk about policies a bit later. But that's the WS addressing endpoint reference. Okay. We haven't finished with the standards yet, but we're having a slight break from them. So, summary so far. Those core WS standards give us the essential support we need. That's the find something, find out about it, call it. That's those ones. And just like everything else, and pretty good tool support, good design for extensibility because you can just throw things in headers, and messages are very verbose, but that's okay, but you need to worry about performance. And messages are not very human friendly, but they don't need to be human friendly because humans don't normally read them. Okay, let's teach the controversy. So alternatives. So we've got this idea, we've got a web-connected world, and we've got HTTP running everywhere. We've got a set of web standards. We've got XML. We've got HTTP. We've got ways of doing things. The services model and the services-oriented architecture model have got nothing to do with SOAP and the web services stack. They're a way of implementing them, but the architecture is orthogonal to what I just talked about. The services, theoretically, you can build a services model using any protocols you want. It's an architectural model, not standards dependent. The standards, if you use them, give you interoperability, which is a really great thing. When this stuff was coming out, I expect that some of the people didn't object that too much to SOAP, but when we go and look at that, so that Wikipedia is this vast list of standards. None of you have ever been involved in standards creation, have you? They're odd creatures, standards people. People who want to spend months and months arguing about commas. I have an aside that I was chief architect, project manager, etc., for an X400 email service. I think we ended up with about 500,000 lines of code, biggish thing. And that was done X400 email service, an OSI standard. And we built it to the original 84 X400 standard because that's what was out there. And the standard was that thick and quite understandable. Then the standards body went away and came back with the next version of the standard, which was that thick and totally opaque. We were experts on that. We just implemented this standard. And you really think, I don't understand this new standard. But it had gone through a standards body and lots of people who wanted to add their particular thought about something. And then you get the standards where, this is optional. In other words, we had a fight. The way we resolved the fight was let you put it in. And we had some of the people I was working with were involved in a SQL standard. So I think I might have mentioned it. So we've got database servers. Cool. There's Oracle, there's SQL Server, there's DB2. And you can access these database servers remotely, which is where most of them are. There's an Oracle server over there. I can open up a client here, boom, and do a query on that Oracle database. What protocol are we running between this computer here and that Oracle database service? And the answer is it's proprietary. If you want to talk to an Oracle database, you use the Oracle protocol. If you want to talk to IBM database, you use the DB2 protocol. It's an obvious place to have a standard, right? Well, there was a standards body called SAG, the SQL Action Group or something, Access Group, SQL Access Group, and one of my colleagues was rapporteur for that group in a couple of years of working and just watching the vendors sabotaging it. Because each of them wanted they all had commercial benefit by keeping their interfaces proprietary. So the company I was working for, we actually did implement that standard because we were involved in its production. And I think two of the vendors implemented it and all the others didn't because it was not their proprietary interest. And I remember Paddy coming and complaining about some of the games that some of the vendors, particularly a large 3-letter acronym one, were playing to try to sabotage things because it was not in their commercial interests. So that's why that protocol isn't there. There was one developed, but it never took off. So, standards committees. So, but that's why I said earlier, this was done by IBM and Microsoft and others cooperating, which was a really unusual thing in those days, because they all saw that they benefited from interoperability. Okay, so you've got this great long list of standards, some of which are used to define other standards, so it's a partitioning question. But the web community, people who go and build web pages and do browser standards, etc., I looked at this and said, this isn't web-like at all. It has nothing to do with the web. You guys don't know what you're doing. So they thought we should be able to build distributed systems entirely using web technologies. Use HTTP rather than just being a transport protocol. We can use the meaning of HTTP to do what we want to do. And there were some very vocal people, often are, with more than a bit of evangelism around there. And some of these people didn't really understand distributed computing because it wasn't their world, but they thought they could do it all. And that enthusiasm was pervasive, so there's good tool support. And these days, a lot of the systems don't support WS star in general, but they'll support the web-based way of doing it, because for a lot of applications, that's good enough and it's lightweight. So, but other applications, the functionality you need just isn't there in these web-based standards. So I probably won't get onto it tonight, but next week we'll talk about the web-based standards, the RESTful standards and way of doing it, and they both have a role in the world. If you just do one, it might be heavier weight than you need. And I suppose some of the heaviness was the people saying, I can do a RESTful thing just by typing it myself. I can type that up and boom, done. And I can't do that with the web services stack because there's so many layers of protocol and so much to do. Well, that's true. But you don't have to, because someone's already implemented it for you as part of the framework you're using. So some of that wasn't particularly meaningful complaint, but they both have a place in life. Here's a pretty slide. It's got colours on it. I like it. It's got colours. I stole that from Microsoft as far as I remember, because I thought I liked the colours. So this is the web services stack. The top stuff in orange is just the business end of it. We've got devices, business processes, enterprise application integration, business-to-business stuff, etc. Then we get down to the messaging layer, and above that is whatever we're going to do to make our messaging secure, reliable, and add transactional support if we need to. The messaging layer is sort of sitting on top of XML, and that sits on top of transports, often HTTP, but could be carrier pigeon if you want to write the standard. And associated with all this is metadata that's describing all that stuff, that's describing policy for this stuff and all the other metadata you need. So that's the basic stack, and it's very colourful. Now we're going to pull out each of those layers. That messaging layer is SOAP with URIs for addressing things, and WS addressing for that more complex version of addressing a service. Way of saying that. So that's what that messaging layer is. Metadata. I'll cross my fingers and remember to say something in a second. Metadata layer WSDL, because we need to describe services, so WSDL fits in there. I've talked about policies. We need a way of defining policy. We need a standard for defining policies, WS policy. We need a standard for attaching policies to other things, because policies get attached to things. So WS policy attachment, that's one of these standards that is used in other standards. Not something you just use by itself. Policy assertion and metadata exchange. Now, if you dug in the pracs, you've dug in and you might have seen MEX around, the MEX. So when you look at the config file for some of the bits of the WCF code, there's a binding area, and in the binding thing is a MEX binding, metadata exchange. And that's how, in that WCF world, you get to find out about things, because it uses that metadata exchange protocol. Now, some of you have probably twigged now that the stuff you've been playing around with in WCF looks a lot like that WS star stack. And the answer is it is. So, historically, in that particular world, there was a component model called COM, which is undoubtedly still busily running away inside this box here. And then there was a distributed computing form of COM called DCOM. And then Microsoft moved to .NET as a programming model. And in that .NET world, they introduced a thing called .NET Remoting, which was pretty much the same as distributed computing model and .NET Remoting. And then they decided we're going to do an entire new distributed computing model in this .NET world, and that's WCF. One of the pillars of Longhorn, which is the only one which actually made it, I think. Oh no, the GUI stuff's there as well. So the WCF was built around these standards, which is why you keep on seeing bits of it around, why it's easy to import and export WSDL, why you define bindings to the metadata exchange in order to see what things are. So that whole WCF stack is built around the functionality that's exposed in this WS star standards. They co-evolved. The WS star standards are more flexible than just these WS. So the WCF implementations are more flexible than just the WS star, which is why you can do other things in there, like run over MSMQ or even REST, but the programming model embedded in WCF is this programming model. So there's a strong association there. So when you go and look at one of those app config files again, you've got the network binding stuff, you've got your binding stuff, and then there'll be another line or so underneath it, which is the MEX definition. Need some security standards. Where do we start? Overall standard. Secure conversation, where I've got a multi-message secure channel. So in the general world, that would be the equivalent of a SSL TLS thing, where I don't just do an expensive authentication secure channel initiation with you for a single message. I do that and establish a secure channel for a conversation, and I pass multiple messages backwards and forwards. So if I was doing that whole order process with quotes and invoices, etc., that would be a conversation that I'd secure. So same to a model that I use with SSL TLS, I do an expensive handshake at the beginning, get a fast symmetric symmetric crypto key that I then use for cheap encoding encryption of the following messages. So, secure conversation, and one could reasonably ask, well, if I've got TLS, I've got HTTPS, why do I need secure conversation? And the answer is because I'm not necessarily running over HTTP. So it's got to have things in the standard which parallel things that are in HTTP web world, because we may not be running over that platform. So that's why that's there. I don't remember what WS Trust does. I have to go and look it up. It's probably one of the ones that's used internally. Security policy. Said we negotiate some aspects of security via policy. Therefore, we need a way of defining that. So security policy defines that. And federation would be to do with federated authentication. So if I've got multiple security systems and the security systems need to talk to each other, that's federated security, and that would define federated security. Okay, security. Reliability, that's a much easier one to talk about. WS reliable messaging. I wonder if I have a... I'll talk about that, and if there happens to be a slide on it, that's a bonus. We talked about reliable messaging last week before, whenever we did message queuing. So if I don't use reliable messaging, I send a request to some service, I have no guarantee that it's going to get there. If I send multiple requests to that server, I have no guarantees that they'll arrive in order. And WS reliable messaging gives me those guarantees. That a message will, if it doesn't arrive, I'll be told about it, but it does it exactly once in order delivery of messages. And then the last ones of these are the transaction coordination, consistency ones, and 3 standards there. WS coordination is the thing that knows about transactional contexts, so the common stuff in the transactional world is in coordination. Because remember when we did two-phase commit, we talked about protocols there with transaction coordinators talking to each other. That's how transaction coordinators talk to each other, is in WS coordination. And then it supports 2 types of transactions: atomic transactions that you know and love, and a compensation-based model called business activity. So there are standards for that. Good, I talked about that. Oh, this is a lovely slide. I thought that had a build on it. Oh, good, it does have a build on it. Back, lovely. As I remember, it took me a long time to write that slide. Okay, so this is an example of policy. Policy's probably been confusing so far. So, I'm going to do the complete build out because that build isn't quite. No, bugger. Okay. So we've got X and Y. X wants to talk to Y with security. So X sends to Y and says, "Give me your security policy." Okay, so let's say this is our authentication policy. So it says, okay, I can accept Kerberos or X509. They're the 2 standards I will accept for security. Okay. So I ask Y for its policy, Y sends me back a message with its policy in it. And then On the client side, on X side, I say, well, here's what I know how to do. Which of what I know how to do and what I will accept are compatible. So it might be that it will accept X509 and Kerberos, but I only do Kerberos. So we can negotiate and settle on Kerberos. So I know what you're capable of doing, I know what I'm capable of doing. Do we have something in common? And if we have, we'll choose one of those. So we do a compatibility check on what I can generate, what you can accept. And if they're compatible, then we will send the response back using a security protocol which this guy has said it will accept. So there's an example. So there's a bit of WSP, so there's a bit of policy boilerplate in WS policy language. It says you must choose exactly one of these. You can't choose both of them. You must choose at least one. So you've got to have exactly one of these. And the security tokens that I will accept will be Kerberos v5 or X509 v3. They are the two security tokens types that I will accept. And that's the definition of the security policy on the server side. And on the client side, again, because we're doing this stuff via policy rather than code, on my client definition, I also have another policy saying, by the way, I can handle this and this. So that compatibility matching will be done in the infrastructure, in the framework. So, and we can say we support auditing. It's an optional parameter, but we do support it. So when we did that negotiation before, the server side would have sent back this saying, I will take Kerberos or X509, and then the client side had to say, which of these two do I support? Oh, I support WebAuth or plain username, password, text. Oh dear, I can't talk to you. In case we wouldn't go any further. But if we have a security token model in common, then when I send the request to you, I will include one of the ones I know you support. So that's how that policy mechanism works. WS security. Okay. Lots of complicated stuff in here. When I next have the chance, I'll dig up that really lovely example I used to use of this type of stuff. And I'm trying to remember who I used to give it to in a talk. So this is where, earlier on in this lecture, I said we support intermediaries. Security supports intermediaries. So the security standards support a model where I want to send something to the tax office, which is private information. But it's going to go through MyGov because I send it to a general federal government clearinghouse, and the clearinghouse is going to send it on to the tax office. And to do that, I want end-to-end security, I want end-to-end confidentiality, crypto, for my message, because I don't want the MyGov people to have access to my confidential information. I want the tax office to get it. So one of the things that WS Security will do is let me do end-to-end security. I can have messages, I can package them up and say, this bit here is meant for this recipient. And although the message is passing through intermediaries, they do not have the ability to decrypt that because they don't have the keys. And the security standards support that. So I can end-to-end security from initial sender through any number of intermediaries to a final receiver, and that's in the standard. I can have a compound SOAP message where some parts of it are readable and digestible by intermediaries and some are not, because I may want to do that. Perhaps the intermediary is doing routing or adding other information to my request before passing it on to the tax office. So a much more complicated model. Have I got... Let me check the next slide. Okay. So the alternative, you think, oh, well, I'll just use HTTPS. Fine. What's the problem here? And HTTPS and TLS SSL are point-to-point models. So if I'm going from my machine to MyGov and MyGov goes to the tax office, each one of those links is protected, but the end-to-end is not protected. It's decrypted when it gets to MyGov. The entire message is decrypted, and then it's encrypted again on the wire to the ATO. But in between, it's in clear text. Whereas these standards let me build end-to-end encryption. So, WS Security, it builds on XML security standards, XML encryption, XML signatures. You know about crypto, you know about signatures, and it lets me implement secure SAT message exchange across multiple trust domains, including going from someone I trust to someone I don't trust to someone I trust again. That's why it says going across trust domains. Right. And I can encrypt and sign individual parts of an entire SOAP message. So it's not all encrypted in the same way. I can encrypt bits of it for different recipients. That's all cool. Signatures are in the header. That's a good place for signatures to be. And propagate security tokens, so authentication tokens can be propagated along with the message securely as well. And because security standards are evolving all the time, then the standards support pluggable algorithms for this thing. They're not, the algorithms themselves are not part of the standard. You say, I'm using this particular algorithm. Everyone know about security. You know what I mean by encryption, signing, authentication tokens. If not, do the security course. But all the things you need to be able to do, and they're summarised there. So there's what a secure SAT message looks like in a simple form. There's our envelope we saw before. There's a header. The header now has something in it. It's got WS security stuff in the header. That includes security tokens, authentication tokens, and signatures for the body and those other tokens. Signatures to make sure they haven't been altered on the way through. And then the body itself is encrypted, and information about that encryption will be in the header as well. I think I can probably skip that. It supports lots of authentication authorization schemes, simple username, password, X509, WebAuth, etc. And said security is done by a policy. You ought to have a standard which talks about how you do the security policy and the standards for that. And I've talked about this basically already, but the idea of policy-based security is take all that horrible complex code out of your code, express it in policies that are interpreted by the frameworks. You make it declarative and administrative, so you put it in an app.config file, and you never see it in your code. You get the request in. When you get the request in, it's been authenticated. The message bodies that are coming to you have been decrypted. You don't do the decryption. You don't do the authentication. The framework does that for you. So your code is just like the stuff you've been writing. It's just the simple business logic, and all that complicated stuff has been done outside because it's done via policy-based mechanisms. If we didn't do it declaratively, then you'd have to write the code, but we do it declaratively. So policy says messages should be signed and encrypted, then signatures get checked, messages get decrypted on the way to the application and the reverse happens, all without any user code. That's cool. One of the common phrases was, SOAP is firewall friendly. Because as people found when they were trying to do communication over the internet, that people have firewalls and lock everything down. And it's very hard to open another port in a firewall because people don't want to open ports in their firewall. Apart from those people who had their systems totally open, but we won't go there. So firewall friendly, so you run things over HTTP, which is totally abusing the whole idea of HTTP, but never mind. You really expect HTTP web requests, not procedure calls. You expect an HTTP message to be something like, fetch the brochure, not update my bank account. It's not quite the expectation of HTTP. So if you're going to run secure services over this, it means you have to implement security properly because you're running over effectively an unsecure network because HTTP is passing through firewalls easily. So tunneling via HTTP means we really have to do security properly, and that's a good thing. So rather than saying, oh, we're running TLS here, the pipes are secure, that's great, you're protecting the bit of wire, but that's very weak security because once you get past the entry point into your system, once you've got past whatever the other end of that TLS connection is, you're now in plain text again and you've got the security's all gone, the crypto's all gone. So this WS model is much stronger because now we're taking the message and protecting parts of it, etc. And that's all good. So if we do message security rather than transport level security, then we can do end-to-end messaging, we can do asymmetric security, so do different things on different parts or requests and response, so we have a lot of flexibility there. We secure that, and we're transport independent. We can do secure message transport over carrier pigeon if we had a standard for doing carrier pigeon transport, because the SOAP and all the other standards are defined in security, not the transport layer. And if we use something like TLS, then that's great, but it's only point-to-point security, and we'll be using exactly the same mechanisms. It's not as flexible. We can't dice and slice the security. You've seen this slide before. Remember, distributed computing is all about reliability, because after all, nothing ever goes wrong. They're all the things that the fallacies. We saw that before. Well, as web services runs on top of networks, and these are networking distributed computing problems, then all those problems arise here. Now, using standards, of course, makes this one go away. If we're running common protocols, then the network is homogeneous because we see a network of services and we don't care how the services are implemented, we just know the interfaces and common protocols. So that's good. We've talked about that. They're autonomous. That's certainly going to bite us. But we're worrying about security. We have to worry about latency, which gives us the chunkiness of our services. And the first one there is the network is reliable, so we have to worry about that. HTTP is built on top of TCP. Is TCP a reliable transport layer? Who would say TCP is reliable? Reliable-ish? Well, compared to UDP, it's really reliable, right? UDP, you throw, whoop, there it goes. And whereas TCP is conversational and you keep track of things, there's acknowledgements floating back, etc. But you can still have network failures. TCP can still drop stuff. You might just drop a message on the floor because things get overloaded. So if you're transferring SOAP requests around via HTTP, then things can still go wrong. It has network goes down, server goes down, things happen. So you don't really want the application to have to deal with those low-level transport issues. And last week we talked about message queuing and how that all went away, because now we have reliable messaging, we can get guaranteed delivery, and if we tick the robust box, we can even get guaranteed delivery across node failures, because we're logging things all the time. So if we want really... So the reliability is a problem, and you can either ignore it and fix up the problems later, or you can invoke a reliable messaging layer which will sit on top of TCP and provide that extra layer of reliability. So let's do that, which is, of course, what WS Reliable Messaging does. And if you look at some of the plumbing you got in the prac work in the last tute that you were using MSMQ, you'll see reliable messaging stuff floating around in there. And some of the words that it uses are also come out of that standard. So you say exactly once, etc., and they're all words from the standard. So reliable messaging standard defines how to do reliable messaging, reliable quality of service over unidirectional, not bidirectional, message sequences. You can ask for exactly once in order delivery. It doesn't do persistence, so it's not really replacement for message queuing. And makes your application programming easy because you haven't got to worry about lost, duplicated, or delayed messages. And it's all built using acknowledgements. So pretty much like TCP. So there's the big picture. We've got SOAP going down through WSRM layer, and we now add an RM header into those SOAP headers. So the SOAP message has envelope headers, and all these extra itty things get popped into the header. And the message doesn't change. We just say, here's my SOAP body. It isn't changing. It's just the request as defined by the WSDL. But all those additional properties we want, reliability, security, etc., are all done by poking things into the header. That's the purpose of the header. Just what you want, some more XML. There's the SOAP message with reliable messaging. So now you'd expect to see in the header, there's the SOAP envelope header namespace. There's another namespace for web services utility, whatever that namespace does. And then there's a namespace called WSRM, which is the reliable messaging namespace. Once we've got those S, WSU, and WSRM namespaces available, we can use them. So here's a SOAP header, and it's got things in there for WSA addressing. So the action we're doing is create coordination context. I guess this is going to be calling the thing we'll talk about next, the WS coordinator. So WS coordination context. That's odd. I think at some stage someone has edited a line out the top there because WSA isn't defined as a namespace. There's not enough namespaces up the top there. No, that's okay, because we're using WSA, but there's no WSA definition up there in the namespace, and there should be. But here's WSRM stuff, message sequences, identifier, and then a message number. So we're sending a message, this is a request, we're sending, that's the name of the thing that we're sending to, and here's the message number. And there's a flag saying whether or not this is the last message in a sequence. So we just put a number on each message that we send out, a sequence number. And then the other side, the infrastructure, not the application, but the other side of the reliable messaging, it will occasionally send us back acknowledgements. So what's the acknowledgement coming from? It's coming from that. And here's our acknowledgement range. We're acknowledging the receipt of messages 1 through 10. That previous one, this is message 10, and now we're acknowledging receipts 1 through 10. If you know about TCP, TCP does much the same thing. We can do block acknowledgements because it's less chatty. So we go request, 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 request. I just got 5 of them. I've got numbers 5 through 10. There we go. So we just do range acknowledgements because it's less chatty. So we're doing, every time we send a request out, we put a sequence number on it in the header, and then the other side is checking these numbers. And of course, if we said we want in-order delivery, then I will get the message, get the message, get the message, but I won't pass any of them onto the application until I get the next message I'm expecting. So if the application has received consumed message number 3 and the messaging layer gets message number 5, it will keep it and not pass it on because it's waiting for number 4. If number 4 doesn't arrive, it'll send something back saying, excuse me, I see missing number 4. And we'll get a resend of number 4. So it's doing, by keeping track of those message numbers, it's doing in-order delivery and it's doing requests for resending of the ones that miss. And you'll do a timeout saying, I really should have received 4 by now. And one of the reasons why you might get messages arriving out of order is because they're not all going through the same network path. Right? We drop it onto the network and magic happens. It goes through this router and then gets switched over to that thing, and the consecutive messages might go through different paths through the network and arrive out of order. And TCP provides that reordering as well. But we can't use TCP's mechanism because we're not necessarily running over it. Coord, good. Generic transactional coordination protocol. It's really just there to do all the stuff that AT and BA need. Yep.
The acknowledgement is the response that you get for the sequence. So
yep.
Acknowledgement is basically the response for the sequence request, or
so yeah, so
upper and lower is
yeah, because when we sent message number 1, request number 1, it got delivered. We didn't get an acknowledgement for that. It kept it because it'd be too expensive to send it back. You're doubling your network traffic. So we just bunch up the acknowledgements. If anything goes wrong, we tell you straight away. But if everything's going fine, we'll just say, oh, we'll send you a batch acknowledgement every 10, because almost all the time it's working properly. So why pollute the network by sending you lots and lots of messages? Is everything good? Everything's good. Is everything good? Everything's good. You don't do that. So, okay, so WS Coord is simply the common plumbing to AT and BA. But by separating into a separate standard, if you had other coordination protocols that you want to implement, you've got a common infrastructure there for it. And it does the things you want. If you think back to the implementation of two-phase commit, we can register transactions. So someone says, hey, I've got a transaction here. We can register the transaction. We can generate a coordination context. We can pass them around. And so it takes care of the general coordination layer that everything else needs. Not a particularly exciting standard by itself. Then WSAT is the atomic transaction protocol. It does exactly what you expect. Two-phase commit, ACID protocol-y stuff, prepare and commit rollback phases. It's intended for short-lived atomic transactions. Everybody must be up and communicating at the same time. You get the normal all-or-nothing complete agreement protocol-y stuff. And it's exactly what you expect. And because it's exactly what you expect, it is only applicable in tightly coupled, trusted environments. There's strong assumptions here about low latency and high trust. It's not the type of thing, Amazon is not going to open an AT, not going to let you go and do AT calls on its services, because you could get a lock and then just go away, and now you've got a denial of service attack. There's a guy I'll talk about next week after, when we're doing some of the services design stuff more, this called Pat Helland. And Pat's a lovely bloke. And I remember being at a workshop when this stuff was being discussed, and Pat came up saying, it's the anti-availability protocol. Because if you implement this and you're putting it on the open web, it's an anti-availability protocol. You'll be wiped off the planet. But Pat's a great guy, and I'll give you some references to some of his stuff. I only know he's worked for two people. I don't know who he works for now. I could find out. So he used to work for Microsoft, doing good stuff, and then he went to work for Amazon, doing good stuff, and he came back to Microsoft, and then he went back to Amazon. The people in that group, they're all in roughly the same part of Seattle, so they just sort of swap jobs with each other. And people you know, and think, I'm not there anymore. I'm not there anymore. I'm back with that. So, but Pat's a Microsoft, Amazon-y type guy, and his real interest is in the design of these internet-scale distributed applications. How do you build robust, reliable, effective, very large-scale applications? So he's got lots of good things to say on that. Oh, there's a complicated picture. I don't think we need to go. In your own time, you can work through that complicated picture. But it's just seeing how AT and WS Coord work together to do all the things you'd expect. And there's a link down there if you want more, if you feel like finding out more details about it. Okay, these standards, yep, widely supported. As I just said, at the whole core of WCF is all this stuff because they co-evolved. And yep, that's all good. And other, I should say Oracle these days, as Oracle bought Sun, but there's lots of tool support there as well. Okay, some references. I'll talk a little bit about some of that. Only really about a couple of them. There's a chapter in Ian Gorton's book on this stuff. I don't know whether I recommend it. I haven't read it for a while. But I think it says everything that I would want to say here. I wrote it, but I haven't read it for a while. So there is a chapter in Ian's book on just this topic. If you don't like what it says, blame the author. Okay? I'll be here next week. You can come and blame me. So that's the reason I'm saying I don't know, because things keep on moving. There's been 2 editions of the book, and I rewrote the chapter for the second book. And what you say in the first edition, you modify for the second, because the world's changing under you. And I think I said the right things about REST. I think what I said is still true, but I might change my mind again if I was asked to do a 3rd edition. And when I was preparing for this, I came across that infoq.com, and there were lots of interesting discussions there as well. A lot of this stuff is stuff that people discuss, and there's lots of blog posts and interesting technical discussions. Okay, now I've got about 3 minutes. Okay. So I'm not going to do very much of this, but I just want to touch on a couple of things. So, and I'm not 100% sure where this came from, because it's not what I got when I did a search for it. But that link at the top is current. That's an Amazon link to their e-commerce service and the programming guide. And there, if you go there, it talks about how to call Amazon programmatically from your program, from your applications. That's all cool. And they support SOAP, and they support REST. And they've supported more of some things than others over time, but there's WSDL there. If you want to find out what services they provide, it's all done in WSDL. And then what you're asked to do in the tube tonight is go and download, using the link we give you, the WSDL from Amazon. and then find a service in that file using Visual Studio. That should work. And because Visual Studio understands WSDL. So you have a WSDL file and you say, look in there for some services. Oh, okay, you've got an Amazon service there. That's cool. And so ports we talked about with WSDL, they're the operations. So Amazon search port, and it's got, that port has lots of operations, keyword search power. So all that stuff should be reflected. And then if you do bring them into the Visual Studio world, what you get is that transformed into Visual Studio. So those WSDL definitions we see here are translated into things like that automatically for you. Okay. Message exchange. When you go and have a look at the app configs, and you'll find that the message exchange. This is probably a good last slide to finish on. So the WCF stuff philosophically is based on that web services world because they co-evolved. But WCF is much more flexible than that. And this is all the bindings that you can have underneath WCF. So here are the bindings. What are the transports used with those bindings? What do the messages look like? And you see a lot of them are actually SOAP. So the default for a lot of the time is net TCP binding, and that's transports TCP rather than HTTP. It's using a binary encoding rather than text-based XML for efficiency, but it's running the SOAP protocol. It's using transport level security. It doesn't provide reliable messaging, and if you're doing transaction flow, it uses the Microsoft OLE transactions way of doing it. So you can go and grab a current version of that table. In fact, I might dig up one for next week. It will have changed a bit, but that's separating out although we've got a model based on that world, when we do the bindings, we have another complicated matrix of what's supported under what issues. So I should dig out another one of those. And I don't think we need to go through those. No, we don't. Okay, it's 5:2. Next week we talk about the REST-based world, and we'll start doing why would you choose one over the other and how they might coexist type stuff. Okay, we're done. Perfect timing. And remember, E1 is away this week, so if you normally attend E1's session,